So in this grade 12 chemistry tutorial, I'm going to go over a bunch of different examples of Lewis structures, show you how to do them. And as we're doing them, we're also going to look at other concepts: orbital hybridization, resonance structures, VSEPR, and exceptions to the octet rule. So let's start with our first example. We're going to start with carbon tetrachloride. Right? And then we're doing carbon tetrachloride. Let's go over how to do Lewis structures first. Let's do that. So what we're going to do is we're going to look at all of the elements. So we have carbon. And we're going to look at how many electrons are available to us. How many do we have to use in our outermost shell? So carbon has 4 available in the outermost shell, and chlorine each has 7. So each chlorine has 7 valence electrons, and we have 4 of these atoms, so we'll do 7 times 4. And if we add up all of these electrons, we get 7 times 4, which is 28, plus another 4, which is 32 total electrons. So then what we're going to do is we're going to take carbon. Carbon is the one that has the most bonding option, and so it has 4 bonding options. So we're going to put that in the center. And then we're going to put chlorine around it with a single bond, starting with a single bond. And we're going to prefer a symmetrical shape. So let's do this. Okay, so we got 1 chlorine here, 1 here, 1 here, and 1 here. And then we want to look at that octet rule, where it says that every atom should have 8 valence electrons to be happy. Now carbon has 8 because each bonding pair represents 2 electrons. So that's 2, 4, 6, 8. Each chlorine only has 2, so we're just going to fill these in with free electron pairs for every chlorine atom. Almost there. All right. So now what we have to do is look at how many electrons we use. So how many used electrons did we use in our diagram, right? If we used not enough or too many, then that's not good. So for each chlorine, we have 6, right? Plus this extra 2. So that's 8. And 8 times 4 is, well, 32. There we go. 32 electrons. So we've used the same amount that we have available. So this is good. So this is kind of the grade 11 format, but in grade 12, I want to sort of explain this further, right? Because we looked at carbon, we said, well, carbon has 4 valence electrons because we're thinking of that Bohr-Rutherford diagram, right? But we know Bohr-Rutherford diagram is not true. We need to look at electron configuration. So if we take that carbon atom and we look at electron configuration, well, we've got 2 electrons in that 1s shell. Then we have 2 electrons in the 2s shell, and we have 2 electrons in that p shell. So let's focus on that outer orbit. So that's the second shell. So n equals 2. We're going to look at these ones. Now notice that s and p are not the same. They're different orbitals. But experimentally, all 4 of these bonds have equal energies. So how do we explain this? So what's going to happen, so let me draw this, just this last shell, n equals 2, on an energy level. So we have that 2s, so we're doing n equals 2. So in the s orbital, we're going to have 2 electrons, 1 upspin and 1 downspin. This is our s orbital. And then we have our p orbitals. There's p. Okay, and we have 2 of them. Hund's rule says we're going to first separate them. Right? We're not going to pair them together until all those orbitals are full. So this is what it looks like. So clearly, these electrons are at a different energy level than these electrons. So what's going to happen is we're going to take one of these electrons and put it into the empty p orbital here. And then we are going to hybridize this, meaning we are going to create a new orbital where we have 4 locations, 4 bonding possible locations where each one only has 1 electron. This is our hybridized sp3 orbital. And in here, we see that we have 4 bonding pairs. That's where these 4 bonding pairs come from, all with equal energy. So this is orbital hybridization, and it explains this. Now let's look at VSEPR. VSEPR stands for valence shell electron pair repulsion. And I said before, we want to look at symmetry, so we put them as far away from each other as possible. And that's what they're going to do. They all have equal energies. They're all going to be equally apart as far as possible, but in a more three-dimensional shape. So what this is going to look like, so we're going to have our carbon atom here. We're going to have 1 chlorine above, and then 3 slightly below, 1 here, 1 over here, and I'm going to draw this little wedge shape. It sort of denotes a three-dimensional shape, so it's coming out of our screen at us. Okay? And then I can do sort of this dotted line shape here, which means it's behind our screen. So with our VSEPR theory, this shape is called a tetrahedral shape. All right, so that's our first example. Let's move on to our second example. So here we got carbonate. It's an ion, so we have a -2 charge. So how we're going to deal with that, just as before, let's look at how many electrons are available to us. So carbon in its outer shell has 4. And oxygen each has 6. And we have 3 of them. But then we have this additional 2 electrons because it is a -2 charge. So we're going to add 2 electrons. So that gives us totals of 4. 6 times 3 is 18. So 18 plus 4 is 22. And then this additional 2 electrons, we get 24 electrons. So just as before, carbon has the most bonding options. Let's put it in the center. And let's go with symmetry and sort of separate our oxygens around it like so. Next, what we're going to do is look at that octet rule. Are all of these elements happy with 8 electrons? Well, carbon only has 2, 4, 6, so let's just add another 2 for now. And oxygen, each oxygen only has 2 each, so let's just put another 6 on each one here. All right, so now to test this, let's look at how many electrons we've used. So used electrons. And here we're going to see a little bit of a problem. So each of these oxygens have 8. All right, so 8 times 3 is 24. That's already 24. And then we have this additional 2. So that's 26 electrons. That's too many. So what we're going to have to do then is we're going to have to get rid of these 2. But in order to make carbon happy, we're going to need to make another double bond with one of these oxygens. Well, the question becomes which one. Let's just randomly choose one for now. And so let's get rid of these and add a double bond here. Now, before we move forward, let's just double check the number of used electrons now. So here we have 8 and 8, that's 16. And then another 8, that's 24. So we have 24 used electrons now. So the number of used and available work out. Now it's an ion, so we're also going to make sure we put in our square brackets and write the charge in the top right corner. But the question becomes, why is the double bond here and not here or here? Experimentally, all these bonds are equal. So what we do is we look at more of a resonance structure. So we look at this double bond here as if it's resonating around all these bonds like this. Right? So imagine a fan that's rotating, right? It's moving all the way around, but if you just look at the fan, it looks like it's everywhere at once. Right? So that's how we explain that. This is a resonance structure. Now online, if you look this up, you'll see that they just put a lot of examples. They just make every one of them double bonds, but I don't like that. It's kind of misleading. So I like to show this resonance structure. Now, according to VSEPR, what shape does this look like? Well, it looks like, just since we separated them all equally, they're just on one plane, and there's 3 of them. So we call it trigonal planar. All right, let's look at our next example. So here we have beryllium chloride. Okay, now this is interesting. What is beryllium doing here? Well, let's look at its outer shell. And to do that, we're going to focus on the outer shell for the electron configuration. So the electron configuration for beryllium is just 1s2, 2s2. So the outer shell is this n equals 2 shell right here. All right, so it has a full n equals 2 shell, looks like this. Right? And there's nothing over here in the p's. So what they do, or what beryllium does, is it takes one of these, puts it into here. And then to make sure that these orbitals have equal energies, it creates our sp hybridized orbital, where we have 2 bonding pairs. So this is also an exception to the octet rule, because beryllium will just be happy with 2 bonding pairs. So we'll put beryllium in the center, because it has the most bonding options here, and 2 chlorines, 1 here and 1 here. So beryllium is happy. Chlorine, to be happy, we need some more electrons here. All right, so that's it. That's done. You can double check your available and used electrons, which would be 16 electrons. So we're all good. Now this shape, according to our VSEPR theory, that looks like a straight line. So we call it linear. Now our next example here, boron trifluoride. Now boron has the most bonding options, but what exactly is boron doing? If we put fluorine here, here, and here, it looks like boron is just not happy. So do we put another pair of electrons to make it happy? Well, let's look at what boron is doing. So its electron configuration is going to be 1s2, 2s2, and 2p1. So this is its outer shell. And let's draw that out here. So we have our n equals 2. We have our s orbital with 2 electrons. And then we have our p orbitals where only one of them has an electron. So what it's going to do, it's going to promote this electron over here. And then it's going to, you guessed it, it's going to hybridize these orbitals into our sp2 orbital, where we have 3 bonding options. So we only have 3 bonding options. Boron is happy with 3 bonding options. This is another exception to the octet rule. So we do not need that extra pair of electrons. Let me just write this a bit to the side because I ran out of space. So we got boron here. And then we're going to have spread out those fluorines. And add our electrons to fluorine. And the shape is as before, trigonal planar. All right, next one. Phosphorus, whoa, 5 chlorines? Phosphorus pentachloride? What's going on here? How does phosphorus do that? It has 5 chlorines bonded to it. That would mean it has 10 electrons with 5 pairs of electrons. How is that happy? Well, let's look at what phosphorus is doing. So the outer shell for phosphorus, I'm just going to do the outer shell. So the electron configuration, when we have n equals 3, so our third energy level, looks like this. So we have 3s2 and 3p3. So there's the outer shell. So what does this look like? So for n equals 3, we have our s orbital with 2 electrons. And then we have our p orbitals with 3 electrons. 1, 2, 3. Now, there is, in our third energy level, the d orbitals exist as well, or could exist. So what's going to happen now is that this electron is going to be promoted to a d orbital. And then, again, you guessed it, they are going to hybridize so that we have 1, 2, 3, 4, 5. There we go. 1, 2, 3, 4, 5 bonding options, each with their electron in it. And this is our sp3d hybridized orbital. So phosphorus is perfectly happy. This is an exception to the octet rule. We're going to put phosphorus in the center there. And around it, how are we going to draw around this one? Well, three-dimensionally, we are going to have one chlorine above and one below. And then we kind of have our trigonal planar going around it. So something like this, where we have a chlorine here, something going behind here, and in front here. So that's our trigonal shape right here, but it's not on one plane. We got something above, sort of like a pyramid above and a pyramid below. So we call this shape a trigonal bipyramidal. And we have angles here of 90 degrees, and between them 120 degrees. And that makes sense. I forgot to mention this, but if we go back to the trigonal planar, this right here, one full circle is 360 degrees. And if we want to spread these out as far as possible, we have three of them. What's 360 over 3? 120 degrees. And then when we have two more, well, we'd want to put one straight up and one straight down, so they are 90 degrees to that plane. All right, next example. Oh my goodness, now we've got six bonding atoms here. On to sulfur. What's sulfur doing? Let's take a look at sulfur's electron configuration and its outermost orbit, where we have n equals 3. So in n equals 3, we have a s orbital and we have a p orbital. So let's draw what that looks like and an energy level here. So we've got an s, so this is 3s, where we have 2 electrons. And then we have our p, where we have 4. So 1, 2, 3, 4. That's our p. And in our third energy level, we can have a d orbital. So let's just draw a possible 5 there. And what we're going to do is going to take this electron and promote it. And we're going to take this electron and promote it. And then, once again, hybridize. So we're going to have 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6 possible bonding options in our hybrid orbital that we call our sp3d2 hybridized orbital. So sulfur can have 6 of them. Okay, how are we going to draw this one? Well, what we're going to do is, let's take sulfur, let's put a fluorine right above it and one right below it, and then we can fit 4 of them around, all at 90 degrees to each other. So let's put one here and then one out in front here. We could take another one slightly out in front here. And another one slightly behind there. Where all angles are 90 degrees everywhere. 90 degrees. And then we just fill up the electrons on all of our fluorine. Now this shape is called octahedral. All right, we got a couple more examples. Water. Let's look at water. How are we going to draw water? So I'm sure you've seen this drawn before. It's going to look like this. We have a hydrogen here and a hydrogen here. So the question is, why is it not linear if we only have 2 bonding atoms onto hydrogen? And that's because if we look at our octet rule, well, one, you probably never realized this, but hydrogen is an exception to the octet rule. And we know why. It's happy with just 2 electrons, because on that first shell, you can only fit in 2 electrons. But here oxygen is not happy, is it? So what it has is it has these free electron pairs. And those free electron pairs have a much stronger push. So they're pushing down onto these hydrogen. And that's going to leave us with an angle of 109.5 degrees. And this VSEPR shape is called angular, or I've also seen it called bent. All right, last example, ammonia. This one, so we got nitrogen, let's put it in the center, and then 3 hydrogens. So you might think that, oh, let's do it as before, similar to how we did boron. However, nitrogen is not going to be happy. Nitrogen is not an exception to the octet rule. So it's going to need a free electron pair. So how is this shape going to look? That free electron pair is essentially going to push that trigonal planar shape downwards, away from it. And so we're going to have something that looks like this, right? So we have this electron pair sitting on top of nitrogen. Then we have this trigonal plate, this trigonal planar type of shape sitting down below. However, because of this push, this angle is also 109.5 degrees. And this shape is called trigonal. And it's got that sort of pyramid look to it, so pyramidal. Alright, so that's it for that tutorial. If you have any questions regarding any of these 5 topics, you can let me know in the comments. And if you have a test coming up, good luck.